In 2025, two of the world's most advanced navies are testing a weapon that doesn't use explosives, doesn't rely on missiles, and challenges how we think about naval firepower itself. The electromagnetic railgun has been promised for decades. But today, Japan and the United States are testing it in very different ways. This isn't a story about who wins or loses. It's about why these tests matter and what they tell us about the future of naval technology. When most people hear the word railgun, they often imagine something futuristic, a science fiction weapon firing glowing projectiles at impossible speeds. Movies and video games have helped shape that image. But in reality, a railgun is not science fiction at all. It is a real technology, based on principles of physics that have been understood for more than a century. To understand why railguns matter and why countries like the United States and Japan continue to test them, we first need to strip away the hype and focus on what a railgun actually is, how it works, and what it is designed to do. At its core, a railgun is not defined by politics, strategy, or even military competition. It is defined by electromagnetism. The basic concept. A traditional gun works by burning chemical propellant. When gunpowder ignites, expanding gas pushes a projectile down a barrel. The faster the gas expands, the faster the projectile travels, but this approach has physical limits. Barrels can only withstand so much heat and pressure before they wear out or fail. A railgun works differently. Instead of using chemical explosions, a railgun uses electrical energy to accelerate a projectile. The system consists of two parallel conductive rails and a movable armature or projectile that completes an electrical circuit between them. When a powerful electric current flows through this circuit, it creates a magnetic field. That magnetic field produces a force known as the Lorentz force, which pushes the projectile forward along the rails. In simple terms, electricity flows. Magnetic fields form. Physics does the rest. There is no explosion inside the barrel. No burning propellant. No chemical reaction pushing the projectile forward. Everything comes from electromagnetic force. Why electricity changes everything? The use of electricity instead of explosives introduces several fundamental differences. First, the amount of energy used to launch the projectile is not limited by the size of a cartridge or shell casing. Instead, it depends on how much electrical power the system can generate, store, and release. Second, the acceleration can be far more gradual and controlled compared to a chemical explosion. This allows projectiles to reach extremely high velocities, often several times the speed of sound, without relying on traditional propellants. And third, the projectile itself can be much simpler. In most railgun designs, the projectile contains no explosives, no rocket motor, no internal guidance system. It is often a solid piece of metal, shaped for aerodynamic stability and heat resistance. This simplicity is one of the most misunderstood aspects of railgun technology. No explosives, what that really means. One of the most common misconceptions is that railguns fire explosive rounds. In reality, most railgun projectiles are inert, meaning they do not explode. So how do they cause damage? The answer lies in kinetic energy. Kinetic energy depends on two things: mass, velocity. While a railgun projectile may be relatively small and lightweight, it travels at such extreme speed that its kinetic energy upon impact can be enormous. This is why engineers often say, in railguns, velocity matters more than warhead size. Instead of relying on an explosion, the projectile transfers its energy directly to the target through shear speed. The physics involved are similar to a meteor striking the Earth, not because of size, but because of velocity. This approach has several advantages. No explosive materials to store or handle. Reduced risk during storage and transport. Simplified ammunition design. From an engineering perspective, it's elegant. From a logistical perspective, it's appealing. And from a safety standpoint, it introduces new trade-offs. Why velocity matters more than size. To understand why speed is so important, consider a simple example. A slow-moving object, even a heavy one, can often be stopped with enough material. But a very fast object, even a small one, can penetrate deeply because it delivers energy faster than materials can absorb or dissipate it. Railguns are designed to exploit this principle by launching projectiles at extreme velocity. The projectile follows a flatter trajectory. Time to target is reduced. External guidance may not be necessary. Accuracy can improve at long range. This does not mean railguns are perfect or unstoppable. High velocity introduces its own challenges, including extreme heat due to air friction, structural stress on the projectile, precision manufacturing requirements. But from a physics standpoint, velocity is the key variable railguns are built around. Common myths versus reality. Because railguns sound futuristic, they are often surrounded by myths. Let's address a few of the most common ones. Myth 1: Railguns are laser weapons. They are not. Railguns fire physical projectiles, not beams of energy. Myth 2: Railguns have unlimited range. They do not. Like any projectile weapon, railguns are affected by gravity, air resistance, and the curvature of the Earth. Myth 3: Railguns are silent or invisible. They are not. Launching a projectile at hypersonic speed generates noise, heat, and visible effects. Myth 4: Railguns are ready to replace all existing weapons. They are not. Railguns are still experimental and face major engineering hurdles. The reality is more nuanced. Railguns are not magic weapons, but they represent a different way of thinking about projectile acceleration. Engineering before strategy. One reason railgun development takes so long is that every advantage comes with a technical challenge. High electrical currents generate extreme heat, rapid wear on rails, electromagnetic stress on components, projectiles traveling at extreme speed face, aerodynamic heating, structural deformation, accuracy degradation over distance. And the platform firing the railgun, often a ship, must supply massive electrical power, rapid energy discharge, reliable cooling systems. These challenges are not tactical problems. They are engineering problems. That is why railgun development is best understood through physics and materials science, not headlines or speculation. Why this matters for understanding 2025 tests. When countries test railguns in 2025, they are not simply testing a weapon. They are testing power generation systems, energy storage technologies, advanced materials, precision manufacturing, thermal management solutions. Each test provides data, not dominance. And that distinction is critical. Railguns are less about immediate deployment and more about expanding what is technologically possible in the long term. Setting the tone going forward. Before comparing national approaches or future possibilities, it's important to stay grounded in reality. A railgun is an application of electromagnetic physics, a test of engineering limits, a long-term research effort. It is not a guaranteed replacement for existing systems, a simple upgrade, a shortcut to technological superiority. Understanding what a railgun really is allows us to evaluate claims, tests, and announcements with clarity rather than hype. And with that foundation in place, we can now look at why navies are interested in this technology in the first place, not as a symbol, but as a tool shaped by physics, budgets, and practical constraints. Why navies want railguns? When railguns are discussed, the focus often drifts toward dramatic speed or futuristic imagery. But navies don't invest years of research and testing for spectacle. They invest in technologies that promise efficiency, flexibility, and long-term sustainability. To understand why modern navies are interested in railguns, it helps to compare them not to missiles or science fiction weapons, but to something much more familiar: naval artillery. Railguns are best understood as a potential evolution of ship-based guns, not a replacement for every weapon at sea. The role of naval artillery today. Modern warships already carry multiple types of weapons. Missiles for long-range engagements. Guns for shorter range, sustained fire. Defensive systems for intercepting threats. Each of these tools has a role, and none of them solve every problem. Missiles are highly capable, but they are expensive, complex to manufacture, logistically demanding, limited in number aboard a ship. Naval guns, on the other hand, are cheaper per use, capable of sustained fire, easier to reload at sea, limited in range and speed. Railguns are appealing because they appear to bridge part of this gap, extending the reach and speed of artillery without turning every engagement into a missile launch. Long-range precision without missiles. One of the primary motivations behind railgun research is the idea of long-range precision without relying exclusively on missiles. Railguns can, in theory, launch projectiles much farther than conventional naval guns. Reduce time to target due to high velocity. Deliver consistent trajectories over long distances. This doesn't mean railguns replace missiles. Missiles offer guidance, adaptability, and complex targeting. Railgun projectiles, by contrast, are often unguided or minimally guided. But for certain roles, such as area denial, long-range warning shots, precision fire against fixed or predictable targets, a railgun could offer an alternative that is simpler and faster to employ. From an operational perspective, this creates options, not dominance. Reduced logistics footprint. Logistics rarely make headlines, but they are central to naval planning. Missiles require complex storage, careful handling, regular maintenance, specialized resupply chains. Railgun ammunition, by contrast, can be smaller, inert, easier to store, safer to transport. Because railgun projectiles typically contain no explosives, they reduce certain risks during handling and storage. This simplifies shipboard safety procedures and potentially increases the number of rounds a ship can carry. In extended operations, logistics efficiency matters just as much as raw capability. A system that allows ships to stay operational longer with fewer specialized resupply needs becomes strategically attractive, even if it is not used frequently. Lower per shot cost, in theory. One of the most discussed advantages of railguns is cost per shot. Missiles can cost hundreds of thousands or even millions of dollars each. Railgun projectiles, being simpler in design, are often projected to cost far less per unit. However, this is where careful framing is important. The projectile itself may be cheaper, but the system that launches it is not. Railguns require high-capacity power systems, energy storage, advanced cooling, precision manufacturing. So while the per-shot cost may be lower, the system cost is significant. Navies evaluate this trade-off over decades, not single engagements. If a system reduces long-term operational costs and offers flexibility, it becomes attractive even if upfront investment is high. This is the same logic used in evaluating aircraft carriers, nuclear propulsion, and advanced radar systems. Compatibility with future ship designs. Modern warships are increasingly designed around power generation, not just weapons. Radar systems, sensors, electronic warfare, and communications all compete for electrical capacity. Railguns fit into this trend because they rely on electricity rather than chemical propellants. Future ships may feature integrated power systems, advanced generators, energy storage modules, modular weapon mounts. In this context, railguns become one possible consumer of shipboard power alongside lasers, sensors, and propulsion systems. This compatibility with an electrically driven future is a key reason navies continue testing railguns, even when immediate deployment is unlikely. It's about architectural alignment, not urgency. Defensive and deterrence roles. Another reason navies explore railguns is their potential role in defensive operations. High-velocity projectiles could, in theory, intercept or disrupt incoming threats, provide layered defense alongside missiles, offer rapid response options. At the same time, the presence of advanced systems can serve a deterrence function not by guaranteeing outcomes, but by signaling technological capability and preparedness. Importantly, deterrence in this context does not mean aggression. It means raising uncertainty for potential adversaries, demonstrating investment in innovation, encouraging stability through preparedness. This is a familiar concept in naval strategy and applies to many technologies beyond railguns. Comparing railguns to existing artillery. To keep expectations realistic, it's useful to compare railguns to conventional naval guns. Similarities: ship-mounted, direct fire systems, sustained engagement potential. Differences: railguns rely on electrical power, higher projectile velocity, different maintenance challenges, experimental reliability profiles. Railguns do not eliminate the need for traditional artillery. Instead, they represent an alternative path, one that may complement existing systems if engineering challenges are resolved. Why navies think in decades? One of the most important things to understand about railgun development is timescale. Navies plan ship classes 30 to 50 years ahead. Weapons integration decades in advance. Infrastructure to last generations. Railgun testing today informs decisions that may not materialize until the 2030s or 2040s. From this perspective, even partial success is valuable. Each test answers questions about materials durability, power management, system integration, operational concepts. And even if railguns never become widespread, the knowledge gained often improves other systems. Efficiency as the central theme. Ultimately, navies are interested in railguns not because they are dramatic, but because they promise efficiency. Efficiency in energy use, logistics, space, cost over time, operational flexibility. Railguns are not about replacing everything. They are about expanding the set of tools available to naval planners. And in modern naval operations, having options, even experimental ones, is often more valuable than committing to a single solution. Transition to the next chapter. Now that we understand why navies are interested in railguns, the next step is to look at how theory meets reality. Because while the potential is clear, the challenges are substantial. In the next chapter, we'll examine how one Navy's early railgun program shaped global understanding and why lessons learned can be just as valuable as deployment. When discussing railguns, the United States often enters the conversation early, and for good reason. The U.S. Navy was among the first to move railguns from theory into large-scale, real-world testing. But the story of the U.S. railgun program is frequently misunderstood. It's sometimes framed as a project that was canceled or abandoned. In reality, it is far more accurate and far more useful to view it as a learning phase. This chapter isn't about failure. It's about experience. Early U.S. Navy railgun testing. The U.S. Navy began serious railgun experimentation in the early 2000s, driven by a simple question. Could electromagnetic launch systems provide longer range and higher speed than traditional naval guns? Early tests focused on proving basic electromagnetic acceleration, measuring achievable muzzle velocity, understanding material stress at extreme power levels. These early experiments were conducted in controlled environments, land-based test facilities, not ships, because the goal was data, not deployment. And the results were impressive. Test firings demonstrated hypersonic projectile speeds, repeatable launches, consistent electromagnetic acceleration. From a physics standpoint, railguns worked. But moving from laboratory success to operational reality revealed challenges that were far more complex than initial demonstrations suggested. The power generation challenge. The first major hurdle was power. Railguns require enormous electrical energy delivered in extremely short bursts. Generating that energy is one challenge, storing and releasing it reliably is another. Early U.S. tests showed that existing ship power systems were not designed for sudden, massive discharges. Energy storage systems added weight and complexity. Power spikes affected other onboard electronics. This forced engineers to think beyond the railgun itself. Railgun testing became a test of ship-wide power architecture, energy buffering systems, electrical isolation and safety. These lessons would later influence broader naval thinking about integrated power systems well beyond railguns. Barrel wear, the silent limitation. Another major issue was barrel wear, specifically rail degradation. In traditional guns, barrel wear comes from heat and friction caused by expanding gases. In railguns, wear comes from extreme electrical currents, physical contact between projectile and rails, intense localized heating. Early tests revealed that rails degraded faster than expected. Precision alignment was difficult to maintain. Maintenance intervals were shorter than desired. This wasn't a deal breaker, but it was a reality check. For a naval system expected to operate reliably at sea, maintenance demands matter just as much as raw performance. Heat management and thermal stress. Closely related to wear was the challenge of heat. Even without chemical explosions, railguns generate enormous heat from electrical resistance, friction, atmospheric interaction at the muzzle. Managing this heat required advanced cooling systems, heat-resistant materials, careful firing schedules. The more engineers pushed performance, the more thermal stress increased, creating a trade-off between speed, reliability, and system longevity. This led to a critical realization. A railgun that fires once at extreme speed is impressive. A railgun that fires repeatedly, reliably, and safely is much harder. Why testing slowed, not failed? By the late 2010s, the U.S. Navy began to slow its visible railgun testing. This change is often misinterpreted. Testing slowed not because railguns didn't work, but because the Navy had learned what it needed to learn at that stage. The key questions had been answered. Can electromagnetic launch reach required velocities? Yes. Can projectiles survive launch? Yes. Can the concept work outside theory? Yes. The remaining challenges were not conceptual. They were engineering, integration, and cost challenges. Rather than rushing toward deployment, the Navy chose to apply these lessons elsewhere. A shift in research focus. Instead of fielding a railgun prematurely, U.S. research shifted toward areas where the knowledge gained could have immediate impact. Hypersonics. Railgun testing provided invaluable data on hypersonic flight behavior, materials under extreme acceleration, guidance challenges at high speed. This directly informed broader hypersonic research programs, not just weapons, but understanding physics at extreme velocities. Advanced power systems. The need to power railguns accelerated research into high-density energy storage, rapid discharge systems, ship-wide electrical integration. These technologies are critical for sensors, radar, directed energy systems, future propulsion concepts, ship-ship integration knowledge. Perhaps most importantly, railgun testing taught engineers how complex it is to integrate experimental systems into real ships. Lessons included space constraints, weight distribution, crew safety, maintenance access, interference with other systems. This knowledge applies to every future naval technology, not just railguns. Realism as a strategic choice. The U.S. approach reflects a broader pattern in military research and development. Not every program is meant to reach deployment. Some exist to reduce uncertainty, test assumptions, inform future decisions. Railgun research fulfilled that role. Rather than forcing a system into service before it was ready, the Navy chose realism over urgency. That decision may be less dramatic, but it is strategically consistent with long-term planning. R&D evolution, not abandonment. It's important to emphasize this distinction. The U.S. did not give up on railguns. Instead, specific testing phases concluded. Resources were redirected. Knowledge was absorbed into other programs. This is how large-scale engineering projects often progress. Aircraft development, nuclear propulsion, and radar all went through similar cycles, periods of intense experimentation followed by consolidation and redirection. Railguns are no different. Why these lessons matter globally? Because the U.S. railgun program was among the earliest and most extensive, its lessons influence how other countries approach similar technologies. Later programs benefit from avoiding early mistakes, setting realistic expectations, prioritizing integration over spectacle. In this sense, U.S. testing shaped not just domestic research, but global understanding of what railguns can and cannot do today. Transition to the next chapter. The U.S. experience shows that railguns are not a shortcut to capability. They are a demanding, long-term engineering challenge. And that context makes other approaches easier to understand. In the next chapter, we'll look at how Japan's railgun testing strategy differs and why starting later may actually offer certain advantages. When Japan's railgun testing enters public discussion in 2025, it is often framed as something new. In reality, it represents the continuation of a very familiar pattern in Japan's defense research: deliberate, incremental development guided by reliability and integration rather than speed or spectacle. To understand Japan's approach, it's important to view railgun testing not as a race, but as a methodical engineering process aligned with existing maritime doctrine. A test-focused strategy. Japan's railgun program is best described as test-centric. Rather than pushing rapidly toward deployment, Japan has emphasized controlled experimentation, gradual scaling, data collection over public demonstration. This strategy reflects a broader philosophy within Japanese defense research: technologies must prove themselves repeatedly under realistic conditions before they are considered viable. In practical terms, this means fewer dramatic milestones, but more consistent technical validation. Each test answers a narrow set of questions. How does the system perform under maritime conditions? How stable is power delivery at sea? How predictable is system wear over time? This focus on precision testing helps reduce uncertainty early, rather than discovering limitations later. Smaller scale, controlled sea trials. A defining feature of Japan's approach in 2025 is the use of smaller scale sea trials. Instead of integrating a railgun onto a frontline combat vessel immediately, testing is often conducted on dedicated test platforms, modified ships, controlled maritime environments. This allows engineers to isolate variables such as saltwater exposure, vibration and ship motion, power fluctuation at sea, crew interaction with the system. These trials are not designed to demonstrate maximum range or speed. They are designed to test consistency and predictability. In naval engineering, consistency is often more valuable than peak performance. Reliability as a core priority. One of the clearest themes in Japan's railgun testing is reliability. From an engineering perspective, a system that performs slightly below theoretical maximums but does so reliably is far more useful than one that delivers extreme performance only under ideal conditions. Japan's testing emphasizes repeatable firing cycles, stable system behavior, predictable maintenance requirements. This aligns with broader Japanese industrial practices, where long-term reliability is often prioritized over rapid innovation. In the context of naval systems, reliability directly affects crew safety, maintenance planning, operational readiness, power efficiency over raw output. Another defining feature of Japan's approach is a focus on power efficiency. Railguns demand significant electrical energy, but Japan's research emphasizes optimizing energy use, minimizing waste heat, matching system demands to available ship power. This focus reflects practical constraints. Not every ship is designed to support massive electrical surges. Designing a system that works within existing power margins increases the likelihood of future integration. Efficiency also supports scalability. A railgun that operates efficiently at moderate power levels is easier to adapt across different ship classes than one that requires extensive redesign. Ship compatibility and integration. Perhaps the most important aspect of Japan's approach is compatibility with existing ships. Rather than designing a railgun first and then asking how to install it, Japan's testing works in the opposite direction. Assess current ship architecture. Identify available space and power. Adapt the system to fit within those constraints. This approach reduces integration risk and avoids costly redesigns later. It also ensures that testing data is directly applicable to real vessels, not just theoretical platforms. Why Japan emphasizes defensive technologies. Japan's focus on defensive technologies is deeply rooted in policy, geography, and maritime strategy. As a maritime nation, sea lanes are critical to economic stability. Defensive readiness supports deterrence. Stability is prioritized over power projection. Railgun research fits into this framework as a potential defensive enhancement, not an offensive shift. High-velocity, non-explosive projectiles may offer future options for area defense, threat interception, long-range deterrence without escalation. Importantly, these roles are explored conceptually and technically, not operationally. Integration with maritime doctrine. Japan's maritime doctrine emphasizes layered defense, situational awareness, interoperability with allied forces. Any new technology must fit within this structure. Railgun testing in 2025 is therefore evaluated not as a standalone capability, but as a possible component within existing sensor networks. Command and control systems. Defensive planning frameworks. This integrated evaluation helps ensure that technology development supports doctrine, not the other way around. Learning from others without imitation. Japan benefits from observing earlier railgun research conducted elsewhere, particularly the lessons learned from extensive testing programs. However, Japan's approach is not imitation. It is adaptation. By starting later, Japan can set more realistic performance targets. Focus on integration earlier. Avoid assumptions that proved problematic elsewhere. This results in a slower public timeline, but potentially fewer surprises. Engineering discipline over headlines. Japan's railgun testing has attracted attention precisely because it avoids dramatic claims. There are no declarations of imminent deployment. No promises of transformational impact. Instead, communication emphasizes experimental status, ongoing evaluation, long-term research goals. This disciplined messaging helps manage expectations both domestically and internationally. What Japan's approach signals. Japan's railgun testing in 2025 signals commitment to technological research, emphasis on defensive readiness, respect for engineering limitations, long-term strategic patience. It does not signal urgency or escalation. This distinction matters when interpreting test results and announcements. Transition to the next chapter. Japan's approach shows that railgun development does not follow a single path. Incremental testing, integration focus, and reliability-first engineering offer an alternative model, one shaped by maritime realities and long-term planning. In the next chapter, we'll look at the core technical challenge both countries face, not policy, not doctrine, but power and energy management. Why energy defines capability. Up to this point, we've discussed railguns in terms of physics, strategy, and development philosophy. But beneath all of those layers lies a single, unavoidable reality. Railguns are not limited by ambition. They are limited by power. More than accuracy, range, or even materials, it is energy, how it is generated, stored, and delivered, that defines what railguns can realistically do. To understand why railguns remain experimental in 2025, we need to focus on electricity, not hardware. Why railguns demand massive electrical power. A railgun accelerates a projectile using electromagnetic force. To do this, it must push extremely high electrical current through conductive rails in a very short period of time. This process requires enormous instantaneous power, extremely rapid current flow, precise control of discharge timing. Unlike conventional weapons that release energy stored chemically in propellant, railguns draw energy from electrical systems that must be recharged after each use. The difference is critical. Chemical propellants store energy compactly and release it instantly. Electrical systems must generate energy, store it temporarily, release it at exactly the right moment. Each step introduces complexity. The limits of ship power generation. Modern warships are powerful, but they are not unlimited power plants. A ship's electrical system already supports propulsion, radar and sensors, communications, environmental control, defensive systems. Adding a railgun means asking that same system to deliver a sudden, massive burst of energy without disrupting anything else. This creates hard limits. Even advanced ships with integrated power systems must carefully balance generator capacity, redundancy, safety margins. Simply increasing generator size is not always possible due to space, weight, and heat constraints. Energy storage versus instant discharge. Because ship generators cannot instantly produce the power a railgun requires, energy must be stored first. This introduces the need for capacitors, flywheels, advanced battery systems. Each storage method has trade-offs. Capacitors discharge quickly but store limited energy. Flywheels are efficient but heavy and complex. Batteries store energy well but discharge more slowly. Designing a system that can store enough energy, release it rapidly, recharge safely, repeat the process reliably, is one of the most difficult engineering challenges in railgun development. This is not a problem of theory. It is a problem of materials, physics, and engineering margins. Cooling and thermal stress. Every time a railgun fires, heat is generated, a lot of it. Sources of heat include electrical resistance in the rails, friction between projectile and rails, air friction at extreme speeds, energy losses in storage systems. Managing this heat requires active cooling systems, heat-resistant materials, careful firing schedules. Without effective cooling, components degrade rapidly. This limits rate of fire, sustained operation, system lifespan. In naval environments, cooling is further complicated by saltwater corrosion, limited airflow, space constraints, material stress at extreme power levels. High power does more than generate heat. It places extreme stress on materials. Rails must withstand high current density, magnetic forces trying to push them apart, repeated thermal expansion and contraction. Projectiles must endure enormous acceleration, structural stress, aerodynamic heating immediately after launch. Each firing cycle tests the system's materials. Over time, even microscopic flaws can grow, reducing reliability and increasing maintenance requirements. Why power systems are the real bottleneck? When railgun programs encounter delays, it is often assumed the problem lies with the gun itself. In reality, the gun is only one component of a much larger system. The true bottleneck is the power ecosystem. Generation, storage, distribution, cooling, safety. Every improvement in projectile performance demands disproportionate improvements in power handling. This creates a non-linear challenge. Small increases in velocity require large increases in power. Higher power increases heat and stress. More cooling adds weight and complexity. At some point, gains become harder to justify. Why simple diagrams matter. This is why railgun testing often relies on diagrams rather than dramatic footage. Understanding railguns means understanding energy flow paths, power bottlenecks, thermal loops, structural loads. These are engineering problems best explained visually, not cinematically. Simple schematics often reveal why progress appears slow and why caution is necessary. Lessons learned so far. Across different programs, several consistent lessons have emerged. Power limits shape design more than ambition. Integration matters more than peak performance. Reliability depends on energy management. Cooling is as important as acceleration. These lessons apply not just to railguns, but to many emerging naval technologies. Why power research still matters. Even if railguns are not deployed widely in the near future, research into power systems has lasting value. Advances in energy storage, power distribution, thermal management. Benefit: radar systems, directed energy weapons, electric propulsion, future sensors, In this sense, railguns serve as a stress test for future naval power architecture. Energy as strategy. Energy is not just an engineering constraint. It is a strategic one. Ships that manage power efficiently operate longer, support more systems, adapt more easily to new technologies. Railgun research highlights how closely technology and energy planning are linked. Transition to the next chapter. Understanding the power problem explains why railguns progress cautiously and why no navy rushes them into service. In the next chapter, we'll examine another critical reality check: engineering versus expectations, and why performance on paper rarely translates directly to performance at sea. Whenever a new military technology captures public attention, expectations tend to move faster than engineering reality. Railguns are no exception. On paper, the idea seems simple: replace chemical propellants with electricity, fire projectiles faster, reach farther, and reduce cost. But in practice, railguns confront challenges that are fundamentally different from those faced by more familiar systems. This gap between expectation and reality is not a sign of failure. It is a normal phase in the maturation of complex technology. Why railguns are harder than missiles. Missiles are complex systems, but they benefit from decades of accumulated experience. Modern missiles use well-understood propulsion, rely on mature guidance technologies, are built on established manufacturing methods, have predictable maintenance cycles. Railguns, by contrast, attempt to solve multiple hard problems simultaneously. Extreme electrical power delivery, hypersonic projectile acceleration, severe thermal and structural stress, precision timing at microsecond scales. Each of these challenges alone would be significant. Combined, they create a system that is difficult to mature quickly. Missiles carry their energy internally. Railguns must generate and deliver energy externally, which ties their performance to the platform firing them. This dependency makes railguns inherently more sensitive to integration challenges. Maintenance realities. One of the biggest differences between laboratory success and operational use is maintenance. In test environments, systems can be inspected frequently, repaired between firings, operated under controlled conditions. At sea, the reality is very different. Naval systems must operate for long periods without major servicing, withstand salt, vibration, and temperature variation, be maintained by crews, not engineers. Railguns place heavy demands on maintenance because rails wear down with each firing. Electrical contacts degrade over time. Heat cycling stresses components. Even small maintenance burdens can become significant when multiplied across an entire fleet. Rate of fire, more than a number. Public discussions often focus on how fast a railgun projectile travels. But for navies, rate of fire matters just as much. A weapon that fires once at extreme speed is impressive. A weapon that can fire repeatedly, safely, and predictably is useful. Railgun rate of fire is limited by energy recharge time, cooling requirements, component wear. Each shot places stress on the system. Firing too quickly can overheat rails, reduce accuracy, increase maintenance needs. Balancing rate of fire with reliability is one of the key engineering trade-offs. Accuracy at extreme velocities. Accuracy is often assumed to improve with speed, but reality is more complicated. At hypersonic velocities, small imperfections have large effects. Air resistance causes unpredictable heating. Structural vibration can affect flight stability. Railgun projectiles must be precisely manufactured, structurally robust, aerodynamically stable. Even then, environmental factors like wind and atmospheric density play a role. Guidance systems can help, but adding guidance increases complexity, cost, and power requirements. This makes accuracy a moving target, one that improves slowly through testing and iteration. Why testing takes years, not months? One of the most common misconceptions is that railguns could be fielded quickly if enough resources were applied. History suggests otherwise. Complex systems mature through repeated testing, incremental improvements, failure analysis, design refinement. Each test answers some questions and raises new ones. In railgun development, testing must account for component fatigue over time, cumulative thermal damage, integration effects with ship systems. These factors cannot be rushed without increasing risk. Lessons from early jet engines. A useful comparison is the development of early jet engines. When jet propulsion was first introduced, engines had short lifespans. Fuel efficiency was poor. Maintenance was intensive. Reliability was inconsistent. Yet over decades of refinement, jet engines became the backbone of modern aviation. The early challenges were not signs of impossibility, they were signs of immaturity. Railguns are in a similar phase. Radar as another example. Radar offers another historical parallel. Early radar systems were bulky and fragile, required constant calibration, offered limited resolution, were difficult to integrate. Over time, improvements in materials, electronics, and computing transformed radar into a foundational technology. Railguns may follow a comparable path, or they may remain niche. Either outcome depends on long-term engineering progress, not short-term expectations. Managing expectations responsibly. For navies, managing expectations is as important as managing technology. Over-promising can distort planning, increase political pressure, lead to premature deployment. Under-promising, while less exciting, allows engineers to solve problems systematically, validate assumptions, build confidence in results. This is why official messaging around railguns tends to be cautious. See trials versus laboratory conditions. Laboratory tests isolate variables. Sea trials reintroduce them. At sea, railguns must contend with ship motion, saltwater corrosion, limited maintenance access, competing power demands. Success in a lab is a milestone. Success at sea is a qualification. The gap between the two explains much of the perceived delay. What maturity really looks like. A mature system is not defined by maximum performance. It is defined by predictable behavior, manageable maintenance, safe operation, integration with other systems. Railguns are progressing toward maturity, but they are not there yet. Recognizing this helps separate realistic assessment from speculation. Transition to the next chapter. Engineering reality often moves slower than public expectation, but it also delivers more durable results. In the next chapter, we'll step back and examine what railgun testing in 2025 actually means, not in theory, but in practical and strategic terms. When news breaks about advanced weapons testing, it's easy to assume that deployment is right around the corner. But in defense development, testing and operational service are very different stages. Railgun tests in 2025 are a clear example of this distinction. These tests are not announcements of readiness. They are signals, carefully measured, deliberately limited signals about capability, intent, and long-term planning. Understanding what they mean requires stepping back from individual systems and looking at the broader context. Testing is not operational service. The most important point to establish is a simple one. Testing does not equal deployment. A system in testing may not be reliable enough for regular use, may require extensive maintenance, may not integrate fully with existing platforms, may still change significantly in design. Operational systems, by contrast, must meet strict standards for safety, reliability, sustainment, crew training, logistics support. Railgun tests in 2025 sit firmly in the first category. They are experiments conducted to gather data, not systems being prepared for routine service. What these tests demonstrate: industrial capability. One of the clearest messages sent by railgun testing is industrial capacity. Successfully conducting advanced tests requires precision manufacturing, high-quality materials, specialized testing facilities, skilled engineering teams. Even when a system is not deployed, the ability to test it signals that the industrial base can support complex projects. For allies and observers, this matters because industrial capacity underpins all advanced defense technology, not just railguns. Scientific and engineering expertise. Railgun testing also demonstrates scientific expertise. The challenges involved span multiple disciplines: electromagnetics, materials science, power engineering, thermal management, systems integration. Running controlled tests means engineers can model extreme conditions accurately. Data collection systems are sophisticated. Iterative design processes are mature. This level of expertise has applications far beyond a single weapon system. Long-term planning, not short-term signals. Another key takeaway from 2025 tests is time horizon. No Navy tests railguns with the expectation of immediate payoff. These programs are designed to inform future ship designs, shape power system development, guide research investment over decades. This long-term view is typical of naval planning, where ships and systems remain in service for 30 to 50 years. From this perspective, testing today helps avoid costly mistakes tomorrow. How allies and partners interpret testing. Allies and partners tend to interpret railgun testing conservatively. Rather than asking when will this be deployed, analysts often ask, what knowledge is being gained? What infrastructure supports this research? How does this fit into broader modernization efforts? In cooperative environments, testing can even encourage information sharing, align research priorities, reduce uncertainty through transparency. The absence of dramatic claims often reassures partners rather than concerns them. Why restraint in conclusions matters. Overinterpreting tests can lead to distorted perceptions. Assuming that testing equals imminent deployment inflates expectations, increases pressure on engineers, encourages reactive analysis. Restraint allows observers to separate experimentation from capability, focus on trends rather than headlines, avoid attributing intent where none is stated. This is especially important for technologies that attract attention because of their novelty. Signaling through process, not performance. Interestingly, railgun tests often signal more through process than performance. Observers pay attention to how testing is conducted, how openly results are discussed, how programs evolve over time. A measured, transparent approach suggests confidence in process rather than urgency to impress. Strategic communication without advocacy. From a communication standpoint, railgun testing demonstrates a careful balance. Information is released to inform, to reassure, to demonstrate competence. But it avoids escalatory language, comparative claims, predictions of dominance. This approach keeps the focus on technology rather than geopolitics. Stability through understanding. Paradoxically, understanding experimental technologies can support stability. When capabilities are misunderstood, they can provoke unnecessary concern. Clear communication about testing phases helps set realistic expectations. Railgun tests in 2025, framed accurately, fit into a pattern of responsible technological exploration. What 2025 does not mean. It's equally important to clarify what these tests do not mean. They do not indicate immediate operational use, replacement of existing systems, sudden shifts in doctrine, short-term changes in naval balance. Those outcomes require years of additional development and evaluation. Transition to the final chapter. Understanding what testing actually means prepares us to look forward realistically. In the final chapter, we'll step back and explore the future of naval firepower, how railguns fit into a broader ecosystem of technologies, and why the future is likely to be evolutionary rather than revolutionary. When we look ahead, it becomes clear that railguns are not intended to replace missiles or traditional naval guns. Instead, they represent an additional option, one that expands flexibility rather than eliminating existing tools. Modern naval firepower is moving toward layered systems. Missiles provide reach and adaptability. Guns offer reliability and sustained fire. Railguns, if matured, could occupy a narrow but useful space between the two, offering high-speed, non-explosive projectiles powered by electricity rather than propellant. This future is less about barrels and more about systems. Software, sensors, and power management increasingly determine what a ship can do. A weapon's effectiveness depends not only on its launcher, but on how well it integrates with targeting networks, energy distribution, cooling systems, command and control software. In this environment, railguns may remain niche, used selectively where their strengths align with operational needs. But niche does not mean irrelevant. Throughout naval history, specialized systems have delivered outsized value when applied carefully. Railguns, if they reach maturity, may follow the same path, not as replacements, but as part of a broader, more flexible approach to naval capability. Railguns aren't about replacing everything we know. They're about expanding what's possible. In 2025, Japan and the United States aren't racing toward conflict. They're testing ideas, materials, and limits. Understanding these tests helps us understand how modern navies think about the future. Carefully, incrementally, and with lessons learned from the past. If you found this breakdown useful, consider liking the video and subscribing for more neutral, in-depth technology analysis. Thanks for watching.